Yes, sir, we are ready to start this today's session.
Okay, awesome. Let me just share my screen. Is my screen visible? Hello?
Yes, sir, it is visible.
Okay, so just so I know, this is completely interactive, right? I can interact with the fellow participants, right?
Sir. Yes, sir.
Okay, awesome. That sounds great. So, all right. So let me just get started off already. It's 2 o'clock. Minimize this. Okay. So thank you for having me. I am Rajat Devadatta Bharadwaj, and thank you for the introduction. So in this today's session, we're going to, be briefly talking about autoencoders and GANs. All right. So now, with that being said, I hope my screen is visible, and let me just present it. Oops. Okay. Yeah. Let me move this aside. All right. So coming to the first slide, I always like to start my seminar with the overview as to what we are going to be doing in the session, right? So this is a 2-hour session, and I was requested to, handle topics of autoencoders and GANs, and few resources, and if there is any question and answers, that as well. I hope we at the end we have some time for the question answers. But nevertheless, we will keep it uh, as focused as possible. And if you guys have any doubts, please write it down so that you can ask me at the end of the session. Because we don't have too much time for the intermediate question answers. So that's why I've kept the Q&A at the end. So we're going to be talking about autoencoders, the theory behind it, and the hands-on. Then comes GANs, the theory, hands-on, and I have this something quite interesting for you guys. I don't know, maybe some of you might know it, and some of you might not. It's called "This Person Does Not Exist." It's a website. I will show you what it does, and then finally we have references and resources, and then Q&A. All right. With that being said, so what exactly are we going to, learn about autoencoders? Now, I said autoencoders, right? But it does not really tell you what exactly in autoencoders. And if you guys are learning something, it's always best to keep, be very focused as to what you guys are going to learn. In the sense that you could see that we'll start off with introduction to autoencoders, the intuition and the general structure, and then hands-on. So we're going to do 2 hands-on using TensorFlow. One is called as basic autoencoder using TensorFlow, and the other one is image denoising. Yeah, so that is what we are going to cover. So buckle up. All right. So for the introduction, and I was told that this is a very interactive session. So I just don't want to be speaking and you guys listening. I want it to be, a co-op, so to speak. So if you, I mean, maybe I ask some questions, or maybe you know the answer. You guys can please answer. There is no right or wrong answers. We're all here to learn. So please don't shy away. All right. All right. So talking about autoencoders, do any one of you guys have any idea as to what autoencoders are? Just to get some intuition. anyone in the background audience? By the way, I'm seeing the students. So if you guys raise your hands, I can just see it. It's not a problem. Maybe yes or no. Okay, all right. So it seems to me that you guys have no introduction to autoencoders. All right, makes my life a bit more easy. All right. So what autoencoders are, as it is being stated very clearly, it's basically a neural network that is trained or attempted to copy its input to its output. So what we're essentially doing is we have some input, right? We can take some array as an input, and then we want the neural network to just give us back the same output. Now you might be wondering, okay, why are we even doing that? I mean, I have the same input already, right? If I pass the same input and I want the same output, what is my end goal here actually, right? That's a great question. If anybody of you had the question. So the idea behind that is we are going to do something called as bottlenecking. I will talk about that in the next upcoming slides, but just we get the theory out of the way. So here it says we attempt to copy its input to its output. Internally, it has a hidden layer. Of course, we all know what hidden layer is. I hope. Yes. 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 Okay. The blue shirt guy. Yes. Good. So we know what hidden layer is, right? So that describes a code used to represent the output. So we have an input layer, and then we have, a hidden layer, and then we have an output layer. So this hidden layer is what we are really interested in. So now continuing on, the network may be viewed as consisting of two parts. First one is an encoder. That's why it's called as auto encoder, right? So automatically encoding something, right? So an encoder function h, which is equal to f of x, and a decoder that produces the reconstruction. So what do I mean by reconstruction here? The output, right? Essentially, it's the output. So what are we trying to reconstruct? Reconstruct the output, which is essentially what? The input itself, right? So we pass in the input to the neural network, and we expect it to give us the same output. That is the reconstruction. And how well does it do? How well does it reconstruct the same output is actually the matter of concern here. So here with this, cute little diagram, you can see that we have X, we have H, and we have R, right? So, what we are trying to actually achieve is we have the input X and we want the reconstruction R with an intermediary H. So what is this H doing? H you can think of as a hidden layer or as the internal representation or as a code. There are multiple ways of calling it. But what is H doing here? So what it does is essentially it tries to understand the input so very well that it reduces the dimension, so to speak. So this is where you guys have to really understand what autoencoders are doing. So we pass in the input X. Now the hidden layer understands the input so much so that it reduces the dimension and then it reconstructs to R. So here we say the general structure of an autoencoder, mapping an input X to an output is called as the reconstruction R here, the input X to the output R with an intermediate representation or code, also called as code, that is the H. Now, if I have to say f is a function of what? F is mapping x to h, and g is what? G is mapping h to r, right? That is the decoder. So the first phase that is mapping x to h is the encoding phase, and the deconstruction, right? The deconstruction that is mapping h to r. So that is g. All right. Now you might be wondering, okay, what is this autoencoder? Now, what type of problem is it? Is it an unsupervised or supervised? Can anybody take a guess? I mean, right now you guys can see, but if you guys thought it was supervised, could anybody maybe tell me why it was supervised? I mean, we are giving the input, right? It should be a supervised learning problem. Can anybody tell me why it is unsupervised? Any idea? Any guesses? Anybody? All right, fine. So it is unsupervised because of the fact that we don't explicitly give the autoencoder or the neural network the intermediate representation, the H, right? We don't give what features to extract out of the given input. We don't specifically mention to the to the model that, hey, these are the features that you need to extract from these given inputs so that you can reduce its dimension. I hope we can. I mean, we're all on the same page. Do you guys understand till now? Yes. Yes. Raise your hands if you do. Yes. I only see blue raising hand. Yes or no? Okay, good, good, good. Okay. I hope now we are all on the same page and we got a brief introduction to what autoencoders are, right? So what are the two different phases? It has an encoding phase and a decoding phase. And it is a unsupervised type of problem. All right. Now, now just to get more intuition so that, and what do I mean by intuition? I simply mean that I have represented with a good picture for you guys, with a picture so that, our brains are, they tend to understand more imagery aspects, right? Rather than just textual aspects. So that's why I've given you guys a picture here. So what it is doing here is you can think of this X as this input layer. Yeah, the input layer, and then the internal representation that was H. You can also call it as a bottleneck. I'll tell in a jiffy why it is called as bottleneck. And the output layer, that is the decoder, right? That is the output layer, also denoted as X cap. So here the input is denoted as X, Xi, or 1, 2, 3, 4, 5, and so on and so forth. And the output is X cap I. Right? So that is the deconstructed or the decoder phase. So bottleneck here. Now, I won't read too much of the data. I mean, the text that I've here. This is I'll be sharing the slides so you guys can check it out. But I'll explain what it is. So this bottleneck is the whole reason why we are doing this autoencoder in the first place. So you can think of bottleneck as something that we are forcing the neural network. We are only giving 3 neurons here, right? Three hidden units, so to speak, right? And we are passing, let's say, 6 inputs, and in the hidden layer we are only giving 3 units. So what is going to happen by default? So here there's a bottleneck, right? We don't have we don't have hidden layer for each corresponding input, but what we have done is we have kind of bottlenecked the hidden layer so that the input coming in needs to go and pass only to these 3 neurons, or these 3 hidden units. Make sense? Yes, everybody are with me? Yes. Yes, I see a few girls in the front row bending their head. I don't know if you guys are understanding or not, but if you guys do, raise your hands. Yes? Okay, fine. So what we are, again, to reiterate, so we have, like, let's say, if I take this as 6 dimensions, we have 6 dimensions, but we are bottlenecking with the hidden layer to only pass in 3 dimensions. So automatically what it is going to, what the models are going to do is, maybe it can take 3 here, 2 here, 1 here, or it is for the model to figure it out. So we don't know what exactly it is going to do, how it is going to do, we don't know that. So the whole point is we pass in the input layer with more dimensions and we bottleneck it. What do I mean by bottleneck? Reduce the dimensions right there itself using the hidden layer. That is, we restrict the number of hidden units so that the inputs pass to those hidden units. And then in the output layer, that's the last dense layer, we, again, extrapolate and deconstruct back. This is also called as upsampling. I don't know if you guys have done convolutional neural networks, CNN. Anybody is aware of CNN? Yes? Okay, great. So what happens in CNN? What is the process of convolution? So why do we even do convolution? It is because we want to, reduce the height and width, right, of the image while increasing the depth. Yes, that is called as downsample. But here, what are we doing after the bottleneck? Here we are again, reconstructing the input back to the same number of dimensions that we passed in the input layer. Make sense? Yes? Make sense? Awesome. Awesome. Okay, great. So now that we, kind of have a little more intuition with, the image and all that, how are we achieving this? So let me just read the middle sentence or the paragraph, whatever you want to call it. This network can be trained by minimizing the reconstruction error. Now, what do I mean by reconstruction error? I hope you guys are able to understand, and it's not a jargon. right? It's not something that you don't understand. What is reconstruction? What is the reconstruction here? Anybody? Okay, I was said this was a very interactive session, but I want some answers. Or is it because of some technical difficulty you guys are not able to answer? All right, fine. The reconstruction error simply means the how much of the model is from reconstructing back the same input. Does that make sense? Yes. Does that make sense? How much off or how much deviation exists from the model to reconstruct the same input? That is the loss, right? So we can see how well or not well it is able to reconstruct the same input at the output. Make sense? Yes? Okay, great. So that is what is reconstruction error. So again, this network can be trained by minimizing the reconstruction error, which measures the difference between our original input and the consequent reconstruction. So that is just the difference between how far it is off from the actual input and the reconstructed input. Now I hope this makes sense, and I hope you guys have understood the whole concept of bottleneck, the intermediary bottleneck or the information bottleneck. Yes. Yes. Okay. All right. Um, Now continuing forward. So now again, just to make it even more simpler and more clear, what are the three different components of autoencoder? So we have the encoder and decoder that we have understood, and we also understood the bottleneck. Yes. So what does encoder do? A model a module that compresses the train, validate, test set, whatever you pass it, input data into an encoded representation that is typically several orders of magnitude smaller than the input data. I hope this makes sense. So the encoder, what it does is it basically takes the training sample and then it reduces the dimension uh, that is several orders of magnitude less than the input data. That is what that's what the bottleneck is all about. So what is the bottleneck? It is basically that component that comprises of this internal representation, right? A module that contains the compressed knowledge representation and therefore is most important part of the network. Yes, right? This is the most important part of the network where it has the intermediary representation or the encoded information, so to speak. And the decoder, of course, we know what it does, a module that helps the network decompress the knowledge representation and reconstructs the data back from its encoded form. Yes, right? I hope you guys understood the three different major components of autoencoder. Yes? Yes? Yes or no? Okay. All right. I wish the session was a bit more interactive and the participants are a bit more involved. Um, but anyway. Now, does any one of you know what PCA is? Principal Component Analysis. Anyone? Yes. Okay. Can you guys put it in the chat box what it is? And I mean, just the whole, why are we even PCA in the first place? What is the point of Principal Component Analysis? Used for dimensionality reduction. That is good. That is good. Sumati, right? Aris. Yes, you guys nailed it. That is what it is. Yes, yes, yes. Okay, great. So now that we know that PCA is used for dimensionality reduction, and we also understood that autoencoders are also reducing the dimensions. Yes, did we understand that? Did that become clear to you guys? Yes. Okay, great. I hope now we are on the same page. But can you tell me what the difference between PCA and these autoencoders are? The major significant difference. Now that we understood. Okay, great. Who's Sumati? You nailed it. Okay, fine. I hope you guys are not Googling. I mean, if you are, anyway, you learned something. Yes. autoencoders are nonlinear compared to principal component analysis or PCA, which is linear. Okay, now the next question arises: what is linear and nonlinear then? What is linear and what is not linear? And which is better? Which is better in terms of the if you want to maybe put this into production, right? Which is better? Which would you end up using? Is it linear or non-linear? The answer is very simple. It's just think of it. Okay, non-linear, non-linear. Great, 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 great. It's non-linear, but for more cases, PCA works fine. That is debatable, or is depends on the type of problem you're doing. But anyway, so the autoencoder, as you can see, that is the green line, is completely non-linear. Meaning, now if I have to fit a line to the data points that I gave to the input layer, right? If I have to fit one generic line that satisfies all the different data points, autoencoder can curve its way and make it fit to most of the data points such that it generalizes and does not overfit. To make, I mean, just be making sure that it does not overfit and it just generalizes well. That is the whole point of autoencoders, right? The intermediate representation or the bottleneck understands the input, the features of the input, such that it fits very well. Well, of course, it depends on the data set and XYZ parameters, but the whole idea behind is it fits very well to the set of data points that we throw to the autoencoders. Whereas principal component analysis or PCA is just non-linear. That means it cannot, swirl its way like this, and it cannot fit very well to the data points. So if it has to do, then we have to draw one tangential line and then calculate the distance between the data points and all that, so on and so forth, right? So it's not really useful. Well, it works fine, but in most of the cases, at least variation on autoencoders or sparse autoencoders, these kind of if we have some kind of use cases like that, then we're better off using autoencoders. All right. With that being said, I hope you guys have got a brief overview to autoencoders. Yes. Yes. All right. All right. Awesome. 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 So now comes the most exciting part. Yes. That is, let's get hands on. All right. Now, I have too many tabs open. All right. Just give me a second. I had my own tab. All right. Is my screen visible? It is visible. Okay, screen is not visible. What happened? All right, now it's visible, right? Okay, great. Now that we have a brief introduction and the intuition of autoencoders, we can just look at an example, right? Now, with the best interest of time, and we still have, um, GANs to cover. I thought it was not the best use of time to code all the code out, but instead, what I am going to do is share this notebook with you guys. And if you guys are interested, you can check it out. But I will go through the major important things that we are doing in TensorFlow in order to achieve what we just spoke about. Um, yes, is that okay? Can I increase the font? Okay, sure. How about now? Asha, can you see? All right. So, with that being said, now let's quickly understand, what we are going to import. Um, of course. So now, just a quick question: how many of you guys have actually done some kind of TensorFlow or written some kind of TensorFlow code, TensorFlow, PyTorch, whatever your favorite uh, deep learning slash machine learning library is? Or is okay? You have written some TensorFlow code. Okay, that is good. PyTorch. Okay. All right. So only two of you guys. Also, how many participants do we have in the room? Just to get some count. Okay, we have about 60. All right, so out of 60, only two people have used it, or three people. Let's turn it off to five. Is that true? I don't think that's true. I think you guys are just shy to tell because you think that I might ask you some question. No, I won't. All right. Anyway, the whole reason I am asking is because it just lets me know how much in depth I should cover. Should I cover the nitty gritty, or should I also, or can I skip it? Right. So looking at this, I think I have to go down a little more in depth, and I cannot skip few parts, which may seem obvious. All right. So now, anyway, with that being said, um, let's start off with autoencoders. So now everybody understood the intuition behind autoencoders, the three parts of autoencoders, why we even want autoencoders. Yes, yes, everybody with me? Okay, great. Now I repeatedly keep asking these questions because I want you guys to be with me, especially because this is post lunch and people tend to do what they want post lunch. And what do I mean by that is people tend to doze off, especially in some theory classes, right? And especially uh, this is a meet, I am not even there physically, right? So more chances of people dozing off, which is we're not really looking for that. All right. Now let's get started. We'll import the TensorFlow and other libraries. That is matplotlib. You know why matplotlib is used, right? Yes. We know the use of matplotlib. Yes. Okay, for graph. Okay, for graph, yes. And then why do we use NumPy, numerical Python? Yes, for data visualization, right? So numerical Python to do some array manipulations and operations and all that good stuff. Of course, who does not know pandas, right? Who does not know pandas? Everybody here knows pandas. Yes, yes. Okay, great. And TensorFlow, yes. So for those of you who don't know TensorFlow or what TensorFlow is, it's basically a deep learning framework developed by Google Brain um, that helps us to create a whole variety of deep learning code. That is, it could be creating hidden units, creating convolution layers, doing auto backpropagation, calculating the gradient, or even recording the gradient, so on and so forth. It's just amazing what TensorFlow provides to us. And if we are really, we keep learning it, then it's we can do so many great things. All right. Fine. Now sklearn, again, who does not know sklearn, right? So we are just importing the accuracy score, precision recall, Intrusion score and recall score. Yes, that we know. And then of course, train test split. If you ever started out your machine learning journey, you would not have done it without from sklearn.model selection import TTS or train test split. Yes, yes. Uh, okay. Then we have so TensorFlow.keras. Of course, if you guys have used TensorFlow, then you guys you must have used keras. So now TensorFlow has completely has a wrapper for keras, and so that's why we're using the layers and losses. I'll get to that. And then TensorFlow is gracious enough to provide us with few out of the box data sets that are quite what do you call uh, quite popular, so to speak. Yeah, predefined, popular, whatever you want to call it, right? So if you ever started your machine learning journey, you're not going to start it without a fashion MNIST or an MNIST, right? So, and that's what we'll stick to today, because it's just easy to, you know, the truth being, it is just easy to manipulate because everything is laid out for us. We don't have to do any data accumulation, pre-processing, and all that. Well, we have to do some pre-processing, but it's just that, right? We don't have to break our heads to do more things. That is why we use MNIST. And then of course we have TensorFlow.keras.models. So we are importing a model. So model is basically a class that you can extend or I mean, if you know what inheritance is, object-oriented programming, we are going to extend the model class into our base class, and then we're going to define it. All right. Now with that being said, now what are we going to do is we're going to load the fashion MNIST. So here we have imported the data set, right? So we say fashion MNIST.load data. So what this does is it basically gives uh, a value of 4 tuples. This is called tuple unpacking. So it gives xtrain, xtest, xtrain, ytrain, and xtest and ytest. Everybody with me? Yes. If you guys have done TTS, you guys know what I'm talking about. So this is called as tuple unpacking, where you unpack 4 variables just directly from one function. All right. And then what we do is we say xtrain equal to xtrain dot as type, and then we're going to convert all of the values to floating type, and then divided by 255. That is just because of normalization. Um, uh, if you guys don't know what normalization is, it's basically way of defining your values between 0 to 1. Now, why are we doing that? It is simply because, see, neurons are not as intelligent as us, right? So the hidden layers are, they don't know. They are not as intelligent as us. So what they might think is, now if a value of 10 and 2 is passed into a neuron, it might think, okay, 10 is greater in value, right? So this must mean that 10 has more value. So I'm going to say 10 is the right answer, right? Even though it has nothing to do, the 10 has no preference over 2, the models or the neurons might just give it some value because it is the face value of 10 is more than 2. That makes sense? Yes, right? So that is why we are going to do some kind of normalization. And then I have not connected my runtime, so I'm just going to connect. I hope you guys have you guys have used Collab. Yes, you guys know how to use Collab, Google Collab, and select your runtime type as GPU, TPU, as you prefer. All right, so now I might get an error. Okay, cool. So I'm just running the first cell. Okay, mute. I think someone has unmuted. Please mute yourself. Yeah, okay, cool. We've loaded that. All right, so now we can see the shape, right? The shape of the X train and X test. So what is X train? Basically, it's the training data that we're going to pass, and X test is the testing data, right? So the shape is 60,000 is going for training and 10,000 is going for testing. And by the way, what is the sample size of MNIST? Anybody knows? I mean, the answer is right here. What is the sample size of MNIST? What do I mean by sample size is how many, that is the, please understand the question. What is the sample size? of the MNIST data set. I'm not asking the dimensions. I'm asking the sample size. It's right here. The total sample size. Yes, 70,000. I hope you guys are not Googling it. Right. Why is it 70,000? It is because right here, obviously we'll want to use the entire data set, right? Some way or the other. So what we're going to do is we're going to use 60,000 for training and the remaining 10,000 for testing. Yes, yes, yes. Fine. All right. That seems good. And fine. Now to define an autoencoder with two dense layers, an encoder. So what do we need? An encoder which compresses the image into a 64-dimensional latent vector, and a decoder that reconstructs the original latent vector. Now, what is the meaning of latent vector? Can anybody guess what is latent here? What is the latent vector here? What exactly is the latent vector here? Yes, 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 exactly. Kudos to you guys. Hidden or bottleneck is the latent vector. Now, what is the meaning of latent? Just in general English terms, latent means something that is exists but you cannot see, right? Something that exists but cannot be seen. So it could be like your atoms, your air molecules. They're all latent. They exist, but you cannot see it. But definitely, they exist somewhere, right? So even in the case of the bottleneck, where we compress the data, right? So the reconstruction or the hidden layer has the reconstruction, that is the code, internal representation, but we cannot see it, but the model knows it. I hope that makes sense. So that's why we call it as latent vector, and we say the dimension to be 64. All right, now comes the interesting part. Uh, now we are defining a class called autoencoder. Now, like I said, where is this model coming from? Where is this model coming from? See, model groups layers into an object with training and inference features. Right. It's coming from, so we said we imported it here, right? The model is coming from TensorFlow.keras.models. We import the model. Great, great, great. So what is the meaning, the Pythonic meaning of this class autoencoder, and in brackets we pass in the model. So what does it simply mean? It simply means that we are extending the model class to our child class. So the parent class is the model and the autoencoder is the child class. And of course, if you guys have done some object-oriented programming in Python, this is Python specific, you have to call it with an init function. So what happens when there is underscore underscore init underscore underscore? Can anybody tell me what happens with this special function or dunder? These are what, by the way, what are these called? Okay, constructor is called. Could you be a bit more specific? By the way, if any function is preceded by two underscore and after two underscore, what is it called? There is a specific name for it. Anybody know? All right, namespace. Well, it's called as the dunder functions. Anybody have heard of dunder methods or dunder functions? D-U-N-D-U-R, dunder, I guess. I might not be sure about spelling, but it's called as the dunder functions. So what dunder functions does is it basically overrides the internal implementation of a specific method. Now you could imagine, now if you say print of something, right? Print of x plus y or 3 plus 4. Now, what is that print actually? Now, print is defined, it's predefined, right? Now, if you wanted to have your own way of your own implementation of print, you could totally do that. How would you do that? Using the dunder methods. So we have to say print or underscore underscore print, and then following maybe maybe you can say hey, this is xyz and I'm printing the variable whatever you pass in, right? So function overloading. Okay. Well, it's really not function. Yes, you could think of it as function overloading, unless it does not have a predefined function for it, right? Sometimes we want to have a predefined function, right? So, all right. So these are called as dunder methods or dunder functions, where it is preceded and forwarded by underscores. And then there are a few methods that you can pass. You cannot pass whatever you want. It only a few predefined methods that exist that you can override. Right. So now with that being said, now what is the super keyword? Super calls the model method. I mean, model classes. It's calling the parent class, and then we are passing this class to the parent class, and of course we know what self is, and then we are initializing. So what happens under the hood is when I call auto encoder and then call it with the parameter that I pass, that will directly come to the init function. Now, where is this parameter coming from? Where have I defined that I need to pass latent dimension? Can anybody tell me where I've defined this? Now, where is this latent dimension even initialized? Can anybody tell me where? Argument for the constructor. Yes, that is inside what? Exactly. So that is inside latent, inside the initialize method of the initialized dunder function. It's not inside TensorFlow. It's inside this init method. So inside init method, I could have few more, named arguments or just arguments as the whole, and I can pass them. And then when I pass them, I need to make sure that I initialize this class with those particular XYZ parameters that I have mentioned. I hope that makes sense. Look, I don't want to teach too much of Python, but this is really needed for you guys to fully wrap your head around this. So we have this latent dimension that when you call it, you have to call it with that variable initialized, and that we are initializing as a local self class variable. And then we have the encoder. So what does encoder do? Encoder basically takes in the input and then reduces the dimension. Yes, yes, yes or no? What does the encoder do? The input layer encoder takes in the input and then reduces the dimension at the hidden layer. What is self role? Can you expand here? Okay. Now, now you guys have used Java. Yes. I think which semester you guys are in? Which semester? 7th semester. Okay. All right. Fine. Now you guys, then I'm sure you guys have used Java. Yes. In Java, there is no function. There is nothing that you could do without class. Yes, without defining a class. Now in Java, fine. In Java, I can take Java example. Forgive me for my CPP. I don't have too much CPP skills. Now in Java, you know this, right? The keyword this. Yes. Yes. The keyword this. Yes. This. Now exactly that is what is being replaced by self here. So Python has its own way of doing things. So instead of saying this dot latent dimension, I'm saying self dot latent dimension, and by passing self as the initialization of argument. So when I say self, right, this is a keyword that has to be defined when you're handling with classes. So when I say self, that gets initialized, and Python interpreter. By the way, Python has a compiler or an interpreter. Basic question: does it compile or does it interpret? Right. So it has an interpreter. So the interpreter immediately knows the fact that okay, this self means it is equivalent of Java this, right? So and whatever self dot followed by a variable name has to be initialized to the class. So they become the class variables. I hope that makes some sense. Yes. Shri, who was that? Who asked the question? Shrikant. Is that clear, Shrikant? All right. Fine. Fine. Awesome. Awesome. It's good you asked and cleared the doubt. So basically, self is uh, just another way of saying this, but in Python. All right. Now we have initialized the latent dimension that is coming in from the parameter, and then we say self.encoder is equal to. Now, if you guys have used Python, then TensorFlow, you guys know that sequential API, you can pass in as a method or as in as a list. Yes, you can create multiple layers as methods or as lists. You guys know this? By the way, if you guys don't know, what it does is basically you can pass in the adding different layers, right? You can pass the input layer, hidden layer, convolution layers, rescaling, resize, augmentation layers, so on and so forth inside of a sequential class. Here it says a group of linear stack of layers into a TF.Keras model provides training inference features on this model. So here, if you look at the example, you can say you can initialize it as sequential first and then say dot add and keep adding, or you can also okay, that is one way of doing it. And by the way, the second way of doing it, or the other way of doing it, is you can, instead of initializing and calling the method add every time, you can just pass in as a list and then keep stacking your layers on top. Does that make sense? Yes. Yes. All right, so now we have flatten. Can anybody tell me what flatten does? What does flatten layer do? I've pulled up the documentation for you guys so that you guys can see and explain. What does flatten do? Compress, convert to an one-dimension array. Yes. That's correct. That's correct. So basically what flatten does is, let's say you have like 3-4 dimension. What it does is it basically takes all the dimensions, multiplies it and converts it into a vector. You should call it as a vector. It's not an array. You should call it as a vector because it's one dimension, right? So you should call it as a vector and it converts those different dimensions into a single dimensional vector. And why are we doing that? Because we want the input layer to be passed as a one dimension vector. Yes, we're not taking in multiple dimensions here. I hope that makes sense. All right, next. So here, so till here, what did we finish? So calling flatten, if you have to visualize, which step did we finish? Did we finish the input layer, the hidden layer, or the output layer? Which layer did we finish now? The input. Yes. That's correct. We have completed initializing the input layer by flattening the inputs, whatever we pass. Next comes what? The bottleneck, right? The information bottleneck layer or the latent vector. So, or the latent dimension. So what are we doing here? It is basically just hidden units. Yes, that's right. So it's basically hidden units with what dimension, or how many number of units do we want? Latent number of dimensions, right? Latent dim number of dimensions. So by the way, what does it take? It takes units as one of the argument, and it takes activation as the other argument. I hope that makes sense, right? So we have defined the latent dimension to be 64. So that means after we flatten, let's say we are taking a vector of 1024 inputs, right? After we flatten that, we have different 1024 inputs that is coming in, and then we are only passing those 1024 to only 64 dimensions or 64 different hidden units. So you can see where the bottleneck is occurring, right? So we are explicitly saying, hey, look, I'm going to take so many inputs, but I want you to bottleneck the in the hidden layer, right? Makes sense? Yes. So that's why we are reducing the we are initializing 64 as a latent dimension and then passing that to our dense unit. Make sense? Yes. Yes. Okay, great. And then activation. Can you tell me, you guys told that autoencoders are non-linear. What aspect of autoencoder makes it non-linear? It's a, if you guys completely understand, you guys understand. Yes, activation function. That's great, Srikanth. The activation function part of it is what actually makes it non-linear. Here, rectified linear unit, or ReLU for short, is a non-linear function, right? Is a non-linear activation function. And again, so what happens if I say non-linear? It simply means that the model is able to fit into different curves, like mentioned here, right? Into different data points. And depending on how we do it, it either overfits or it underfits or it just generalizes pretty good. I hope that makes sense, right? We have finished the encoder layer. If we come back, we have finished these two, right? We have the input, flattened it out, and then we have the bottleneck. Make sense? Yes. Now what is left? What is left? The output or the decoder or the deconstruction layer. Yes. Great, great, great. You guys are in sync. Now, what is the whole point of the output layer? How do we want the output layer to be? The same dimension as the input layer. Yes. Yes. Yes or no? Great. Just a second. Yes. So now, where did the 784 come from? Can anybody take a wild guess? Or maybe if you know, yes, exactly. It came from 28 by 28 or 28 times 28. Okay, now where did the 28 come from? Yes, exactly. The image input, because we have the dimension here is what? 28 by 28 with 60,000 samples. And the test is 28 by 28 with 10,000 samples. So now I'm passing by flattening, right? So I'm going to pass this 28 by 28 and the flatten layer, what it'll do? Okay, so you pass this 28 by 28 dimension. What I'm going to do is multiply and make it a 780. How much is it? 784, right? Yeah, 784 dimension uh, hidden units, and then pass it. And then those hidden units get passed to, sorry, those units gets passed to those hidden units. Again, further reducing the dimension to only 64 units. Make sense? And then in the decoder, what I'm doing, I want to reconstruct the same input. So after the 64 hidden units have been, taken and, kind of understood the input, extracted the features and have fit really well to the input. Now the output portion is to reconstruct it back. And what do I mean by reconstruct it? Get me back those 784, reconstruct it back to those 784 units. And then what do I want? Obviously, I cannot just take one single line vector and then visualize it into an image, right? Image, at least you need 2 dimensions. Make sense? So what I'm going to do is that 784, I'm just going to reshape it back into 28 by 28 dimension. Yes, makes sense. Height and width. Makes sense. Yes. Yes or no? Great, great, great. Okay. Now, we have the call function that takes x as the input, x is the input. Then we are going to call the different layers encoder. So that is defined with self.encoder. So we're going to call it. By the way, if we call it, what happens? Now I say self.encoder of x. What is internally happening? What does it do? Anyone has any idea what it does? Maybe main function, constructing sequential class object. Okay, no. What it does is print. Okay, so it calls self constructor. No, guys. What it does is, now what is encoder? Self.encoder. What is encoder? It is a type of tf.carriers or sequential, right? It is of tf.carriers or sequential. Now, sequential is a class. Yes, we all agree sequential is a class. Why? Because simply S is beginning with a capital. And of course, all the classes begin with capital. That's the easiest way to know if it's a class or a function. Now, all right. Now, when I say self.encoder of x, now whatever x I pass here gets forwarded to encoder, and now encoder is basically like a function that I can call because of the sequence TF.character sequential method, or I mean the class. I can call it as a function itself, and then what happens is when I call it as a function, it does one forward pass. Make sense? Yes. What is forward pass? Forward propagation. What is it? Pass to sequential as forward. Yeah, but what is forward pass? I want an answer for that. What is forward pass? We have, right, forward pass and backward pass, back propagation, stochastic gradient descent, back propagation through time. Yes. What is forward pass? Take inputs and pass it to the next function. Uh, Weights input to the hidden layer. All right. So forward pass simply means that this X is going to get passed to this flattened and then gets passed to this dense. Simple as that. Right? It just does one forward pass. It's that simple. So whatever X I'm going to pass, since it's the encoder class, the layers.flatten gets called on that input X and layers.dense get called on that input X, thereby calculating what? The cost function. Yes, at the end, the cost function is calculated. And then what do? What do we do at the back pass? We do differentiation. Yes, we do back propagation. We update the weights and what? Weights and bias. Yes, weights and biases. So after one forward pass, so what forward pass basically means is, if you guys have used TensorFlow or even PyTorch, I'm sure you guys might have heard this model.predict, right? Model.predict, that the function. What does the dot predict do? The dot predict basically calls like this. That's it. So dot predict just takes the input and does one forward pass. And then we compile and calculate the loss and update the weights through over iteration. We keep doing that, and that's when your model gets keep updating weights and biases, and then that's when your model reaches or fits to the data points pretty good. Yes, weights are updated and finally prediction would be done. Yes, yes, yes. All right. Now can I get an explanation for this? Can I get an explanation for this? Decoded equal to self.decoder of encoded. Okay, now I'm passing X here. X is the input. X is the training set or the actual input. But why am I calling encoded? Does not make sense. Can anybody please answer that? What is this actually doing here? Until done prediction from hidden layers, next pass. Could you please rephrase? Takes the reduced vector and passes it to the reconstruct. That's correct. That's correct. So am I calling encoded on the decoder? Exactly. Bottleneck as the input. If you see the pipeline, what is the pipeline? The pipeline is input. That is the 784 different inputs passed to the hidden input layer, and then we do bottleneck, and then we reconstruct it back. But what is the input for the output layer? What is the input for the output layer? It's the encoded value, right? Yes. But what is the hidden layer? It's the encoded value. Now, just to be sure, our encoder contains of the reconstructed, sorry, not the reconstructed, the encoded values because of this dense layer, right? This dense contains the internal representation or the bottleneck or the code, whatever you want to call it. And that is internally contained or self-contained in the encoder. Yes. So that is why the output of encoder will be till the bottleneck, and the input to the decoder is basically the bottleneck itself. So that's why we are going to pass the decoder, the input as encoded. And then what do we want? Do we want the encoded value or the decoded value? Yes, input plus hidden is equal to encoded. Exactly. So yes, we want the decoded value, right? That's good. So that is why we want to return the decoder. Now what happens is, now I'm going to instantiate a variable to a class, and I'm going to pass in the latent dimension how much ever I want. So when I do that, now the init method will instantiate it. Now the latent dimension gets instantiated, self.encoder and decoder gets instantiated. Now the compile, of course, we know, right? We want to compile the model. That's when we can update the losses. So autoencoder.compile. So we're going to just do random optimizer, and losses is mean squared error. This is more a question for your deep learning teacher. Don't ask me. And then, of course, autoencoder dot fit on what? What am I fitting the this autoencoder on? On the train and test, right? Sense. By the way, am I passing? Sorry, train and X train and X train. By the way, am I passing? Am I passing any output? Am I passing any output to this? Saying, hey, okay, if this is the input, this is what the output should be. Yes. Am I passing anything like that? No, right? So we are not passing, or we are not telling the model explicitly that if a particular X is given, this is what you should the Y be. So fit yourself to that model. I mean, to that data point. No, right? So we are not doing that. But what is the input is same as the output. That is why we are fitting on X train. Usually, what would it be? Y train, right? X train and its corresponding Y labels. Yes, Y train, right? But we're not interested in that. We want the same exact output. So that's why we say X train underscore X train as input as well as outputs. And epochs, I think you guys know what epochs is. Basically number of complete one forward and backward pass. Yes, iterations is quite ambiguous. Just make sure you say it's one complete forward and backward pass. And I have a question from Asha. Based on what is it 64? Okay, this 64 is really arbitrary. You're free to choose whatever you want. But the whole point is we want to reduce the dimension, right? We want to create a bottleneck. So we don't want to give too many hidden nodes or hidden units, right? So we tend to keep the hidden units quite low, but at the same time not too low so that the model, cannot understand a thing, right? It cannot, even extract the values. It needs to be less, but it, you guys have to do some tuning for this. That's where I'm sure you guys must have heard about hyperparameter tuning. Yes, HPT. Yes, hyperparameter tuning. Yes. So that is where this comes into picture, and this is just arbitrary. You guys can select whatever value you want. All right. So we and what does the shuffle do? Anybody? What does the shuffle do? Shuffle. What does it do? Shuffles the data set order. Exactly. Awesome. Awesome. You guys are nailing it. Awesome. So basically the shuffle, if it's set to true, now whatever I pass won't come sequentially. So it won't be like one after the other. So it'll be X will be replaced to Y, Z will be replaced to A, and all that shuffling will take place. Why are we doing it? Because we want to maintain the generalness of the data set. Sometimes what might happen is the data set might be skewed, maybe in ascending order or descending order or in some kind of pattern that if that pattern exists, maybe the model might overfit to that pattern, right? So we don't want that. So that's why we shuffle it and make sure that there is no skew in the data set and there is no trend that is being followed. It is just completely random and you have to figure it out on your own. So sort of like that. And then validation data, of course, we want to validate on the X test. And of course, the Y corresponding is again X test. I hope that is clear now. Now it's going to train. Now, since I'm using my GPU, I mean, using the collab instance of GPU, it's quite fast. I keep the epochs to a nominal level because I don't want to bore you guys with this. But anyway, you guys can see the loss, the validation loss, and all that good metrics. So while that's being done, let's continue. Now the model is trained. Let's test it by encoding and decoding images from the test set. All right. So encoding images, obviously, how do we want the image, right? So we want the image just like how we passed it. So we have to encode it to X test, right? And then we call numpy. What does this numpy do? So basically what it does is, any idea before I give it away? What does this dot numpy do on a particular this is a TensorFlow object. Converts to numpy array. Okay, from what? Okay, why are you making the model fit to training set? Uh, Wait, why are you making the model to fit for training set only? Is it because of the accuracy? Okay, what is your question? So you mean why am I fitting to X-train and X-train? Is that your question, Shrikant? Yeah, can you tell me why? I think I explained it. Or can anybody else tell me why? Why am I fitting it to X-train and X-train? That's the whole point, right? Unsupervised learning, same input and output. Yes, yes. Because what are we trying to achieve? We are just trying to achieve, we pass in the input, we introduce a bottleneck, that is the dimensionality reduction, and then we reconstruct it, uh, the output, right? Because the input layer should be output. Is it correct, sir? Input is, yes, yes, yes. Because the input, we are expecting the same output. Please understand that whatever we pass in as the input, we are expecting is at the output layer the same output, right? The input should be equal to output. But how well does the model kind of produce the same output is the question here, by reducing the dimensions. Input is reconstructed. Yes, I hope that answers your question. Why am I fitting to X-train and X-train? Yes, makes sense. Everybody, great. All right. Now, yeah, the question. So people, what were the people saying? Converting it to array. Uh, okay, converts it to numpy array. I think I got only one answer. Well, yes, converting it to numpy array, but can you be a bit more specific? From what? From what? And what is the point of doing this? Can anybody tell why? I think I kind of dropped off, I guess. My apologies. Okay, to reduce the pixel values, reduce the size. Okay, well, the point is now if I just say autoencoder.encode of X test, that is one forward pass on the X test, what it does is it returns a TensorFlow tensor. Makes sense? Now, what is a tensor? Anybody quickly? We're kind of running out of time. What is a tensor? Anybody? What is a tensor? We say TensorFlow, right? But what is the tensor part of TensorFlow? Anybody has any idea? Scalar. Okay. More answers. Optimized vector for TensorFlow calculations. Okay. Matrix. High level mathematical functions. Okay. So the tensor part of TensorFlow simply means okay, it's an n-dimensional array. It's that simple. So even you don't usually call up until 3-dimension as tensors because we can call it as 3-dimensional matrix. But anything beyond 3 dimensions, right? That we don't have we usually don't deal with so much dimension matrix in day-to-day lives, right? Even if you were doing, let's say, matrix multiplication, you usually won't deal with, let's say, more than 3-dimensional matrix. Make sense? Yes. Yes. So that's where tensors come into picture when the dimension is beyond the nominal dimension. And what do I mean by nominal dimensions? From 1 to 3. So from 1 to 3, it's basically 1 is a scalar or a vector, 2 is 2 dimension, 3 is 3 dimension, and then you guys can say you don't usually call it as a matrix. You should call it as a tensor. It's basically tensor is basically the definition of tensor is n-dimensional vector, or sorry, n-dimensional matrix. It's an n-dimensional matrix. All right. So till here, if I were to do it, TensorFlow will automatically cast any kind of array to a tensor, right? That is the whole point. It will make sure that it is operating as a tensor object and not as a NPy array object. Even if the dimension is 1, it will convert it into a tensor object because that's how TensorFlow works. So up until here, if I would have said it is just a TensorFlow tensor of whatever dimension the output is. But if I say dot numpy, what I'm saying is from the TensorFlow tensor of that dimension, convert the same thing into a numpy object or a numpy array. Why am I doing that? Because the reason is simple. You remember I imported matplotlib, right? What is the whole point? To plot some images or to plot some arrays, right? Now matplotlib does not actually support tensors. It only supports numpy arrays. So that is the whole point of doing this. So what it does is it casts the TensorFlow tensor to numpy arrays. And this dot numpy is not provided by numpy. It is provided by TensorFlow itself, TensorFlow library itself, to convert the TensorFlow tensor into a numpy array. Does that make sense? Yes. Yes. Why did we convert the TensorFlow tensor to a numpy array? Does that make sense? Yes. TensorFlow.numpy. Yes. 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 Exactly. So of course, if we do whatever we do on encoder, we do the same thing on the decoded image. So decoder of the, so obviously now we have to make sure that we don't pass X test here. We have to make sure that we pass the encoded version of, right? That is what the decoder expects. And then we cast it to a numpy object. And then now if I run this, all right, now this is some plotting. Where did it go? Yeah. Now you see this plot is basically the above is original and below is reconstructed. You see what happened. Can you guys like, make, should I zoom in a bit more or is it visible? Can you guys see what has happened? Okay, I see most of you guys, not, I mean, where is the screen? Is the screen on your phone or is it on your, because I see most of you guys, nodding your head down, keeping your head down. Okay, it's both. Okay. Okay, somebody has a question. Where is the call invoked? That's a great question. I was waiting for someone to ask me that. Can you guys take a guess? Where is this call actually invoked? Can you guys take a guess? Where is this call invoked? Is it invoked here? Is it invoked here? No. This call method, whatever implicit. Okay, where is it invoked? Is it invoked right after I instantiate the class? Auto encoder. Implicit. Okay, somebody has got the answer right. It's when I call model.fit or autoencoder.fit, because that is only the time it makes sense, right? Only when I say fit, what does it actually do when I say fit? It simply means whatever value I'm passing, take it and pass it to my encoders, or take it and pass it to my model or the neural network, right? That's the whole point. So that is when I call autoencoder.fit, the call method gets called. Does it make sense? And that was a great question. I don't know who asked. Mochita Vijayan. I hope I am getting your name right. Right. So that was a great question. So when I call the fit method on my model, that is when the call method gets called. All right. So now you guys can see the original and reconstructed, right? It seems like it has done a pretty good job in reconstructing back the bottlenecked image. Yes. Yes. Yes or no? So you guys saw how easy it is to do some kind of dimensionality reduction in such easy way. And what was the, I mean, how much code did we write? We hardly wrote. I mean, we imported libraries, imported the data set, then that's just like 20-25 lines code, and then we're already able to see how well the model is doing, right? That's great. That's great. Now there's a second example that is called as image denoising. But sir, how can I use the decompressed image? What do you mean? Okay, so my question is, why do you actually want to use the de? Oh, okay. So my question is, I think I got what you're trying to ask. So, okay, now I've compressed it, but at the end of the day, I'm uncompressing it back. What is the point, right? Is that your question? I don't know who that is. Anurag. Great, great. That's a good question. So let's see, for those who did not actually understand the question was, okay, I am getting an input layer. Now I'm going to compress the input to some kind of bottleneck, and then but during the output I'm uncompressing it back and getting the again the dimension back, right? I mean, what is the point? Like, where is this where is the bottleneck even coming into picture? Where am I actually using it? That's a great question. And to that my answer is, it depends on how you use it. It depends on how you use it. So you could, what you could essentially do is you can create a model with the bottleneck and just save those weights. Make sense? Just save those weights of the model bottleneck. And then when you want to reuse it, of course, you need to uncompress it back. But the whole point of doing this is it will save you some memory when you save it into your when you flush it into your hard disk or whatever. This bottleneck, of course, will save you some memory compared to the output layer or the input layer. Does that make sense? Does that make sense? So what you need to do is you need to find a way to serialize this bottleneck into some kind of some kind of array or whatever, or even a TF record that could have that could work, and then you can save it into your disk. And when you want to use it, you need to reconstruct it back. It is just like doing. It is just like doing. Okay, when I want to pass the image to a model which is of 28 by 28, I'm going to flatten it and then pass it, right? I'm not direct. I mean, yes, if you're doing convolutional neural networks, you are going to pass the image directly, but at the end layer, you're obviously going to flatten it anyway. After the convolutions, you will flatten it, right? So the whole point. So what you're doing is you will flatten it, but then reconstruct it back. So the whole point is when you flatten it, or when you create a bottleneck, that's when you have to save the model. Make the hidden layer as the output to be used. Uh, I didn't get your question, sir. Make the hidden layer as output to be used. Could you please rephrase? But that is the whole point. So when you create a bottleneck, serialize this and save it into a disk. And when you want to reuse it, reconstruct it back. That is the whole point. To use the compressed image. Okay. But I hope I answered your question. Yes. Again, it depends on how you want to use it. But of course, we cannot use the, I mean, even in the PCA, right? We reduce the dimension, but when you want to actually use it, we reconstruct it back. So we find the distances between the data points, and then of course we draw a tangential line and all that good stuff. But the whole point is we reduce the dimension, and then we can save those reduced dimension into a disk, and that thereby you are reducing basically the maybe even half. Maybe if the data set size is 24, you might get away, but with 10 GB of data set once after it has been once after it has been bottlenecked. All right, that's some great questions. All right, now looking at the time, I only have till 4 o'clock, and I still have one more topic along with some coding to finish. So I thought I could finish this, but it took some time. But nevertheless, I want you guys to go through this. The second example of auto encoding is to use image denoising. So what is image denoising? It's basically, we pass in an image with complete junk and complete, we corrupt the image basically, right? We corrupt the image and then we pass it to an autoencoder that gives us back the reconstructed image without the corruption. See, that is the whole beauty of autoencoders. Now, again, another answer to your question. We could use autoencoders for these kind of implementations as well. So, what is the whole point you asked? This is the point where you can pass in some corrupted data and you can get the reconstructed data back. And by the way, how many of you guys know Tesla? Yes, Tesla car. You guys know, right? I'm sure everybody might know. Yes, I don't know why you guys are not raising your hand. So now, obviously, Tesla uses state-of-the-art object detection, recognition, blah blah blah, semantic segmentation, all that good stuff, right? All that good stuff. Yes, yes. Now, if I were to say it's easy to break Tesla, how? Just get inside the image. Now, whatever image is coming in from the camera, just corrupt it. And what do I mean by corrupt it? Just add some noise to it. Just multiply that array. We all know that image is what? It's basically 2-dimensional, 3-dimensional image, right? Sorry, array, right? An image is a 2 or 3-dimensional array. Yes, yes. So what I'm going to do is I'm going to just multiply that array with some random noise, that is 0, 1, 2, or like whatever it could be, right? I'm just going to add some noise to it. What do I mean by adding noise? Just multiplying the original image array with some random values, right? So when we do the matrix multiplication, obviously the entire image would not have been gone, but we would have definitely induced some kind of noise to it. That is corrupted the data. Now, when you corrupted the data, now obviously machine learning algorithms are, they, even though it looks photo, it takes a look at the photo, but at the background is just doing numerical computation, right? Matrix multiplication. Yes. So if we send the corrupted data, now if I ask the model to predict on the corrupted data, what do you think is going to happen? What do you think is going to happen? Did you guys get my question? Yes, raise your hand if you did. So what do you think is going to happen? Right? Some answers, come on. What do you think is going to happen to the Tesla car, to the Tesla self-driving car? Blood image will be processed. Okay. Yes, I mean, ideally that is what is happening. But if we were not, take into consideration all these nitty-gritty, we could easily hack the Tesla system and make it take actions that is completely undesired. So because the image is not clear, it has to predict some output, right? Instead of saying take left, or instead of saying take right, it might end up end up doing the complete opposite. It might just go straight or just hit the brakes or do something that is not really recommended. I hope that makes sense. Yes. So that is another way where we can, even if we pass a corrupted image, we get the reconstructed image back. So I won't go too much in detail, but of course we are going to use the MNIST fashion data set again. And then I'm just going to talk about this. So denoise, of course, we are instantiating and then calling the model as the parent class. And then of course, we don't have any constructor parameters here. So we just call the denoise without any arguments. And then we obviously take in the input. So what we are doing here is we are using convolutional neural network to reduce the height and width. That is to get the convolutions, to get the image convoluted. And then, so what happens during convolution? So convolution phase creates a bottleneck. Yes, because convolution means reducing the dimensions. Now, if you were to do the opposite of convolution, what is the opposite of convolution, guys? What is the opposite of convolution? Can anybody answer this question? Deconvolution. Okay.
Deconvolution.
Also called as? Matrix transpose. Yes. Convolution transpose. Make sense? Yes. So the opposite of convolution is deconvolution, but also called as the convolution transpose. So what convolution transpose does is in convolution, we obviously increase, we say 16, 32, 64. But in convolution transpose, I'm not sure why I'm saying, I think this should be the reverse. My apologies. So it should be, no, wait, correct. because well, that's all right. The whole point is, when you do convolutions, what you do is you maybe say 32 and the next convolution be 64, 128, so on and so forth, right? When you do that, what happens? The height and width gets hard by every convolution. Make sense? Yes, if you guys know what I'm talking about. So the convolution transpose does the exact opposite of this. In convolution, the height and width gets reduced while the depth increases. But whereas in convolution transpose, the height and width increases by reducing the depth. Does that make sense? Now, why are we increasing the height and depth? Because we want to reconstruct the image back. So that is, please go through this code. You'll know exactly what I'm talking about. So we'll do the convolution to create a bottleneck, and then we'll do the convolution transpose to create, to reconstruct the image back. And then, we get the output and so on and so forth. It's just only so much remaining. So please go through that. I'm running a bit short of time. Decoder is the convolution transpose. Yes, exactly. That's great. That's great. Yes. So I'm happy people are understanding what I'm trying to say. All right. So now, all right. Now comes a bit more theory. Now I hope everybody understood about autoencoders, right? Yes. Yes. The basic autoencoder and the convolution autoencoders. That's great. So give your round or give yourselves a pat in the back for understanding complex topics. That's good. Fine. Now the next topic is, of course, GANs. GANs to me is one of the favorite interesting topics. So again, what are we going to learn about in GANs? So introduction to GANs, GANs algorithm, teaching equilibrium, and basic DC GANs, that is deep convolution GANs hands-on. All right. So are you guys excited? Who's excited? Nobody is excited. I mean, if you guys are excited, you guys have to raise your hand fully. Why is this like, that does not show enthusiasm. Yes. Fine. Awesome. Now GANs. What is the full form of GANs? Anybody know? Data generation. Okay. Yes,
Generative adversarial network.
Yes, generative adversarial network. And thanks to me, I've given the answer right here. So, all right. So GANs, or short for generative adversarial networks, are a class of machine learning techniques that consists of two simultaneously trained models. Please bear with me. I'm reading the text here. One that is trained to generate fake data, and the other that is trained to discern the fake data from the real examples. All right. Now, so GANs basically means that we have a generator, we have discriminator. So what is this adversarial? Adversarial means one is opposing the other, one is against the other, right? That is the adversary here. Now, for the generator, the adversary is the discriminator, and for discriminator, the adversary is generator. Now, what is this generator and discriminator? I'll tell you. So the whole point of GANs is that now there are two active participants. One's job is to create fake data, right? One's job is to create complete fake data, and the other's job is to see that created data, whatever that is, or the given data, is it fake or not fake? Does it make sense? Yes. How cool is that? One is opposing the other. All right. So we have one generator that whose job is to basically create fake data. All right. And we have the discriminator whose job is to basically analyze whether the given image or the data, is it real or fake? Make sense? Yes. Yes. Does it make sense? All right. One is fake, one is real. Yes. So now the job of generator, I like I said, it takes in the, here if we take a look at it, now here is the first step, that the actual training sample, this could be your digit MNIST that passes to the discriminator. And then the second step is we pass some random noise to the generator. Okay, this generator produces or synthesizes some sample based on this random noise or the array that is passed. And then we pass both of these to the discriminator. Now the discriminator will check, hey, what is the, is it real or fake? It just basically gives a binary output. Is the given image real or fake? That's it. And then of course, we do classification error and iteratively train. And over a period of time, we come to a point where the generator is producing real images and the discriminator is unable to identify whether the image is real or not. at best it can take a 50-50 guess. All right, so that is what the basic intuition of GANs are. So I won't read too much. You guys can just go through this PDF if you guys are interested. All right. Now the subnetworks. So what exactly happens step by step, and what is the input, output, and goal of these two networks? So the generator and the discriminator we have, and then the input. What is the input for the generator? So we give some random noise as the input for the generator initially. And what is the input for the discriminator? Like I said, can anybody tell me what is the input for the discriminator? Input for the discriminator. Please don't look at the screen. I know. Real data and or yes, the output of the generator. So it could be real data and or the output of the generator. Make sense? Yes, yes, yes. Okay, great. So here it says discriminator receives input from two sources. One is real from the training set and other is fake from the generator. Okay, what is the output of generator? To create fake examples that strive to be as convincing as possible. Basically creating something that is fake, but it is as good as new. I mean, as good as original. Basically, your fake notes, right? People have mastered how to create fake, fake check or fake. I mean, what do you call it? Fake notes, currency notes. Yes. So that is the generator, and the what do you call it? The money counting machine. It also tells us whether the note is true, or I mean whether the I don't know why I'm not able to make sentences. It also tells us why the notes are, I mean whether the notes are original or fake, right? Yes, yes, right. So that is the job of the discriminator. That's it. So predict the probability that the input example is real or fake. Fine. The goal, what is the goal of the generator? Uh, Generate fake data that is indistinguishable from members of the training data set. Makes sense? So basically creating something that is as good as the ones that was there in the training set. That is the real set, right? And the discriminator, our goal is to distinguish between fake examples coming from the generator and the real examples coming from the training set. I hope that this makes sense. Yes? Do you guys understand? Yes or no? My audio changed. Is it okay now? Okay, okay. My apologies. All right. All right. Now, I just want to quickly take you through the GANs. Now, you guys understood what GANs are, generative adversarial networks. What are the two components? One is the generator, one is the discriminator, right? Now, what is the goal, the input, output, and all that we understood. Now, how does this actually work? This is the beauty. How does it actually work? So now let's quickly talk about the discriminator first. So what is the time? Time right now is 3:30. All right. 2:31 to be precise. Okay, now let's quickly talk about the discriminator. Now, now for the discriminator, what are we passing? We are passing the training samples. See here it says, take a random real example X. So do keep in mind that X is the real example and X star is the sample synthesized from the generator. So that is basically fake. Yes, makes sense. So X is the real input, X star is the fake input generated from the generator. All right. Take a random real example X from the training set. All right. Next, generate a random noise vector Z and using the generator network synthesize a fake example. Like I said, now what is Z? Z has nothing to do with this training set. We're not even passing training set to the generator. We're just passing some random noise that is basically random matrix, 2-dimension, 3-dimension, whatever it could be. Right? We're just passing that random matrix to the generator. And then we are expecting it to do just one forward pass. Just saying, hey, predict this on this image. I know it has nothing to predict, but only when it predicts, calculates the loss, backdrops, and then again the cycle continues, right? That's when we get to some good accuracy, right? So that's what we're doing. We're synthesizing from the generator based on the input C called X star, and then we're passing that to the discriminator. Now the discriminator job is, see, it says use discriminator network to classify X and X star. Now till we understood, till here we have understood. Next, obviously, an error. We're going to use at the end. We're going to use sigmoid. Yes, sigmoid layer. Sigmoid layer. And then we're going to compute the classification errors and back propagate the total error. So I hope you guys understood, right? So what exactly happens here? We pass in the real set, we pass in the generator set, and for generator the input is some random noise, and then we synthesize that and we get the output. We pass the outputs of the generator and the input from the training set to the discriminator. Now it takes these two input and sees whether the input is real or fake, and then gives us the classification error, and then that trains the generator. All right. Now this is for the discriminator. What about the generator? Now the beauty, the most important, aspect of this is whatever the classification error we get. Now the discriminator says, hey, this is actually false or this image is fake. Now, should I take that and train the discriminator, or should I take that output and train the generator? Could anybody answer this question? Now the discriminator has given me the output saying this is 0, that is fake. Okay. Now I'll take that to train my generator, or I'll take that feedback to train my generator or train my discriminator. That feedback is important. Why? Generator, right? Yes, exactly. Why? Because if the discriminator says it is fake, then that simply means the generator is doing a real bad job. Yes, it's doing a terrible job, that the discriminator knows it is fake. The image is fake. Make sense? Yes. Yes. Make sense? Yes. 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 So that's why whatever the output the discriminator gives, I'm going to give that as a feedback to my generator. All right. Now for the generator, what happens is, of course, we're going to take the input, generate a new random noise vector Z using the generator network and synthesize X star. Again, what is X star? The fake image or the fake samples, right? And then pass that to the discriminator to classify X, then compute the classification error and update the discriminator now. Now, obviously, we also need some metrics to update the discriminator, right? Makes sense? Because you cannot just blindly trust the discriminator, because you don't know whether the discriminator is correct or wrong, at least in the initial stage. Make sense? Yes? Yes or no? So what we do is we are going to, get the classification error and then feed that back to the discriminator. I know although this might seem very easy to understand, it's kind of counterintuitive as to how you're actually going to achieve this. So that is the beauty of GANs, and that is why this is really what I really like doing. All right, so compute the classification error and backpropagate the error to update the weights, update the generator weights and masses, seeking to maximize the discriminator's error. That's the whole point, right? Now, see, now discriminator does not have to, generator does not have to produce completely fake images, if and only if the discriminator is doing a really bad job. Make sense? Yes. Now, what I'm trying to say is the generator does not really have to produce a fake image exactly like the real one, if and only if the discriminator is basically bad, is doing a very terrible job. Because I know discriminator is wrong, and it is obviously going to give me wrong outputs. Yes, make sense? Make sense? Great. All right. So either maximize the discriminator error or minimize the generator error. Makes sense. And for this also, either for discriminator, either maximize the generator error or minimize the discriminator error. It's either or. So it's either maximization or minimization problem depending on what you're looking at. I hope that makes sense. Now you might be wondering, okay, fine. Now it keeps on, iteratively training, and now discriminator gets better, generator gets better, and all that. So when do I come to a stop? When do I know that, okay, a discriminator is good, that in the sense that it is producing a real, images that is close to the real one, and the discriminator is good in identifying whether the image is fake or not fake. Can we ever reach a point of minima with these two when they are competing against each other? Can we ever reach a point of concurrence, or can we ever reach a point of consensus? What do I mean by consensus is, um, where both of them agree. Can we ever reach a point there? Why not both? Could you please elaborate, sir? Anurag Sharma, both agrees. Can we ever reach a point of minima? And what do I mean by minima is where generator is generating samples that is so real, and discriminator is properly discriminating whether the image is real or fake. Can we ever reach that point? Well, it's kind of counterintuitive, right? I mean, if I say it can reach, then is discriminator doing a really good job? Because if I say, if the discriminator says, okay, this image is real, but it is actually coming from the generator. Now, what happened there? But we know that the image is actually generated by the generator, but the discriminator says it is real. So there again, discriminator is doing a bad job. But again, now if the image is fake, and the discriminator says it is fake, is the generator doing a good job? No, right? So generator has to reduce the classification error so that the image is generated as close to the possible. But how does generator sample the data as it is sampled from random noise? The search space is large. Okay, see, you're looking at the search space like that. We're not searching for it now. We are not searching here. So what are we doing here? We are trying to we are doing back propagation. So what happens in back propagation? It's not random, right? I mean, yes, it might seem random, but after iteratively, it comes to the point of minima, right? Yes, makes sense, Mochita? So it is not that the search space is large. We are not searching for anything here. We're just trying to come to a point of minima. Makes sense? And we know the truth because we are actually taking the samples from the training set as well. That is how the image even gets generated in the first place. Make sense? Because we have something to look at, something to see for. That is how we know that, okay, the image should be like this. And if it is not like that, train, keep training. So when it is training, only the weights and biases are updated. It's not searching randomly here and there. I hope that makes sense. So we cannot really reach a point of equilibrium where both are correct, because one is counterintuitive of the other. Make sense? If the discriminator says, hey, this is false, then generator is doing a bad job. But if the discriminator says it's true, then the discriminator is doing a bad job. I hope you guys kind of understood the whole point. Yes. And what does this relate to? Does this bring any light to you? I mean, what does this resemble? Anything? Does this point of contradiction or confliction, does it remind you of anything? Yes, no? Okay. So we have something called as game theory. Have you guys have heard about it? My question was, what does this remind us when there is no point of minima? That is, one is against the other. One is against the other, and we cannot reach a point where both are satisfied. So, okay, there is something called as game theory, where it is called as a zero-sum game, where the one player's demise is the beneficial for the other player, right? So if one player fails, that means the other player has won. So that is a zero-sum game. So that is what is actually happening here. So either the generator has to win, or either the discriminator has to win. Both cannot win. That is a zero-sum game, and this is exactly this is more of a game theory problem. First player will play, and second player will wait. Um, I don't know what you mean by that, but the players who are competing in together, they're not competing one after the other. They are competing together. So that's the whole point. All right. Now there is something called as Nash equilibrium, but I mean, we know that we cannot reach a point of minima or consensus, but what we can reach is something called as a point of acceptance, right? We have to accept, because at the end of the day, we want the generator to produce greatest images that the discriminator cannot recognize. It is fake. All right. So that is where the Nash equilibrium comes into picture. Does anybody of you guys know what Nash equilibrium is? Of course, we all understand what equilibrium is, but Nash equilibrium, if you guys don't know, is a point at which neither entities can improve their situation or pay off by changing their actions. So no matter what you do, you cannot change your situation. I mean, you cannot get better than this. Yes, it's a level of saturation. Exactly. So, and we can reach the Nash equilibrium, but it's not as easy to say, okay, the GANs has reached Nash equilibrium, right? So when does GANs reach Nash equilibrium? When the generator produces fake examples that are indistinguishable from the real data, right? But the discriminator can at best randomly guess whether a particular example is real or fake. Now, when the discriminator is trying to predict, it becomes a 50-50, right? Because the discriminator cannot exactly, or with 100% accuracy, or even with 90% accuracy, it cannot predict. Because if it does, then generator has to get better. It's that simple. If the discriminator says with 90% accuracy that, hey, this image is fake, then the generator has to get better. It's that simple, right? So we are kind of skewed towards the generator getting better than at the discriminator. So whatever, once the generator gets excellent, that is, it's indistinguishable from the real data set, the discriminator, even when you pass that image, at best, it can just take a 50-50 guess. Doesn't make sense? Yes? Yes? Is this topic interesting? Yes? Yes or no? Yes. All right. So now that is the theory. So what did we go through? So we went through the introduction, subnetworks, I mean, the internal workings. We went through the algorithms of the discriminator, of the, of the generator. My apologies, I didn't change it here. Rookie mistake. And then reaching equilibrium. All right. Um, now let's get hands-on, right? So again, now time is 3:45. Currently the time is 3:45. All right. Now again, I mean, I have to shut it down by 4. So let me quickly go through this. So again, the introduction, what are GANs, the generator, the artist, and the discriminator, the art critic, of course, right? The discriminator is the critic who says, hey, your generation is fake. And the generator is the one who tries to generate, realistic images. So here we have the generator, the artist, a neural network trying to create pictures of cats that look real. And then the discriminator, thousands of, see, that's what the discriminator is, the one that dictates how the image should come, even though even though initially we're just passing some random noise to the generator. And the discriminator, the art critic, a neural network examining the cat pictures to determine if they are real or fake. Now during the training process, what happens? Let me just zoom in zoom out a bit so that. All right. Now, in the first attempt, the generator is just doing something random because, of course, we have instantiated with some random noise. Does that make sense? Yes. And then the discriminator clearly says, hey, this is, it's not even close to real. Next, after many attempts later, okay, it is back propped and it is kind of coming to that shape of the cat. But still, discriminator is good enough to say, okay, this is not even close to being real. But then after like several more attempts later, now generator has mastered how to generate so realistic image that the discriminator thinks at the end of the day that it is the correct image. But do keep in mind the discriminator is actually wrong here, and we have not reached a point of consensus, right? So that is the whole point. Now again, I'll just go through this. Of course, we are again doing the same imports. Matplotlib, NumPy, Python imaging library, just to, the GIF. You can see the GIF here, right? GIF, how you call it? Uh, GIF or GIF, it depends. I call it as GIF. Sorry, GIF. Yeah. So you can see the images being produced after a couple of iterations. And then if you wanted to learn more about GANs, you can see the Intro to Deep Learning course by MIT. That is a great resource if you guys wanted to learn more about any of the topics, reinforcement learning, generative models, self-driving cars, LiDAR, whatever, there's so much, and it is coming from an authentic source such as MIT. So please feel free to use this resource. I don't think I've put this in the resource section, but I can send it in the chat box. All right. With that being said, we have our basic imports. And then, of course, we are going to use the MNIST dataset, that is the handwritten dataset. Don't confuse this for the fashion MNIST, where we have different shoes, dress, all that stuff. We are using the handwritten MNIST. Then the train, we are just doing some kind of pre-processing. Of course, we know all of this. If you guys look into it, you guys can understand. And then we are rescaling it. That is, I mean, the normalization part of it between 0 to, I mean, -1 to 1. All right. Then the batch size, buffer size. Again, this is feel free to explore. Um, now, now what we're doing is this is basically tensor, right? So we want to say dataset.from tensor slice, pass in these images, so that becomes the training datasets, and we are going to shuffle it with the buffer size of 6,000. Sorry, 60,000. So what happens is, obviously when we shuffle the dataset, we need to take into account, let's say at least 32, 48, or maybe even 256, right? So we can't just keep shuffling one at a time, especially when the sample size is 70,000. It takes forever. So shuffle with some buffer size and create a batch of batch size. That's what this is doing. It's just one liner. All right. Now, if we quickly go back. All right. Fine. Let me just try to explain this. So what we are doing now, so the whole point of achieving this is to use convolutional transpose. Like I said, convolution transpose does the inverse of convolution. And the way we are going to create a generator is we are going to initially, lay out the dimension 7 by 7 by 256, and 256 being the batch size, and the 100 is the input shape. And then we do batch normalization. For those who don't know what batch normalization is, it's basically, like we do normalization on the data set, right? So scientists and researchers have figured out that if we do a normalization on the layers itself, on particular bunch of layers itself, it tends to produce better results and better accuracy. So that is why we do batch normalization. And we use nonlinear activation function, that is the leaky relu. Please feel free to use whatever you want. And then this is basically a dense, right, of 7 by 7 into 7 into 256 that you could reshape by to 7 by 7 by 256. That becomes 7 height, 7 width, and 256 as the depth. So now we can assert to check if the shape is what we want. Now in TensorFlow, if you guys have used it for CNN and whatnot, the first comes the batch size, right? Next comes the height, width, and the depth. That is the color. Makes sense? Yes. And by the way, when I say depth, that is the color, the RGB color. Yes, makes sense. Yes. Okay. So here the none means the batch size. We have not specified any. Do keep in mind that this batch size is not, don't confuse this batch size for the batch size of the shape, right? We are just shuffling with the batch size of 256, that's all. All right, and then we add, now the way this works is that we add convolution to the transpose, and of course we have to go down in size, right? In convolution, we say 32, 64, 128. For transpose, we're doing the exact opposite of this. So we do 128, 64, 32, and so on and so forth. And what is this 5 by 5? Can anybody tell me what 5 by 5 is? Any idea? Any idea? Kernel, yes. Now, if I were to okay, I'm not connected to the runtime. I don't think I can connect because I can only run one instance and I need to shut the other instance down. But basically 5 by 5 is the kernel size. For those who don't know kernel, please ask your deep learning teacher. They might be, I mean, they'll help you out definitely. And with the stride of 1, so if we set the stride to 1, we are not going to be reducing the what do you call it, the depth size, so to speak. Sorry, not the depth, the height and width. If we set the stride of 1, what happens? Obviously, right? If the dimension is like, let's say 7 by 7, with a stride of 1, we're not really neglecting um, any pixel, so to speak, right? So that's why if we keep the stride 1, you're not going to upsample in case of convolution transpose or downsample in case of convolution. Does that make sense? The whole point of convolution is to downsample, right? Or get the convoluted image. But if you set the stride to 1, it's not going to do that. It's going to stay the same. All right. And then again, the same thing gets repeated. We do batch normalization and add the leaky ReLU. And then again, we add one more convolution to retranspose and set the strides. Now here we want to reduce the dimension, right? Reduce the dimension for the generator. So that's why we set the stride 2, 2. So sorry, not reduce the dimension, increase the dimension. My apologies, not reducing. We are increasing the dimension. So we are upsampling. So that's when if you pass in a 7 by 7 image, it gets transformed to here 14 by 14, but the width or the sorry, not the width, the depth gets reduced. So it would become 128, 64, so on, so forth. Yeah, see here it's 14, 14, and 64. So what happened here? Here, since we did a stride of 1, it did not really change the shape of the image. But when we set the stride of 2, 2, we just, what does this assert do? It basically checks the if given value is equal to another value. That's it. So we are just asking the model dot output shape is equal to none, 14 by 14, 64. So by 14 by 14, here is the upsampled image size, and 64 is the depth size. So what happened here? So convolution 2D transpose upsampled the image and made it into a from 7 to 7, it doubled it, right? To 14 to 14, while halving the depth, that is the channel. Does it make sense? Does it make sense? Yes. Yes, yes, yes. Please follow. These are little intricate details that we tend to miss out, and especially if it's starting out, these are all, just goes above the head. And then finally, we have the last transpose. Of course, we do batch normalization, ReLU, and then we have the last convolution 2D transpose. And then, since it's the last layer, we don't want to do any more convolution. We are happy. I mean, we want to do convolution, but we just don't want to change anything else. So we are happy with the one convolution operation. And then, of course, when we do the convolution operation, we get 28 by 28 because the stride is set to 2 by 2. If the stride was to be 1, it would be 14, 14, while halving or reducing the convolution size. Now, if I set 1, obviously the depth gets reduced to 1. Does that make sense? That is why we want 1. Now, what happens here? Now you can see how this we formed an image out of nothing, right? This was just some random value that we passed. And then from there, we formed an image of size 28 dimension. I mean, 28 by 28 with the color of 1. Does that make sense? So if I say color of 1, what is it? Is it RGB or grayscale? If I say this 28 by 28 is the height and width, and the color or the depth, what is it? Is it RGB or grayscale?
Grayscale.
Yes, exactly. Grayscale. Grayscale. Great. So of course, none by height and width and the RGB. I mean the depth. That is the grayscale. And then we return the model. Here we make the generator, instantiate it, create a random noise, and then we pass that noise and set train equals to false because we don't want to train it right at the moment. We just want to do one forward pass so that we get some kind of weights, right? We get some random weights initiated. And then, okay, I need to run it to show you guys time on all. All right. This is running. Meanwhile, let's. So that's what. So here we created a random noise that is this Z. See this random noise that we created the Z, and then and then call that noise on to the generator that we did one forward pass, and we made sure that it is not into training mode. What does that mean is it does not track the gradient. It's that simple. I mean, it's basically what it is doing, because we just want to see what the image looks like. This is the image that looks like 20, looks like this. So it's some random noise that got generated, right? And we set the color map to gray. We just plotted using the matplotlib.plt, that function. And then now comes the discriminator. Now the discriminator is simple. It's a sequential API. Now, like I said, we could do the same thing using this, and then we could just say layers, the same thing we could just copy paste it. But I just wanted to show you different methods of doing, because previously I showed you the list way, and now this is one, the add, calling the add method. So we have layers.convolution 2D. Now, what are we doing in discriminator? We are doing convolution operation. That it takes 64 convolution with this kernel of 5 and stride of 2, right? And the input shape that we pass is 28 by 28 by 1. Now, obviously, it makes sense, right? Why? This is 28 by 28 by 1, because the output of the generator is 28 by 28 by 1, and also the output of the training shape is, of course, I mean, if you've worked with MNIST, it's again 28 by 28 by 1, right? With the batch size of none or 0. So that's why we do that, and we add dropout layers to do some regularization so that we don't overfit. I hope you guys know, right, what dropout layer is used for. Yes. Yes, great. So we add dropout layers so that we don't overfit the model, and then we at the end we flatten it and then get the output 1. Now, why is it 1? Can anybody tell me why is it 1? Yes, the dropout is for to avoid overfitting, but at the end we get the output, the dense unit 1, right? So why is it 1? Can anybody take a guess in the discriminator? Any guess? Any guesses? Okay.
Real or fake?
Fake. Yes.
0 or 1.
Exactly, 0 or 1. So we just need one unit to whether give me 0 or 1, right? And we can change this thing. We can add a sigmoid layer at the end to just give us the probabilistic output between 0 and 1, right? And then, so that's why we keep dense to 1 and then return the model. And then the discriminator, of course, just like how we instantiated the generator, we're going to instantiate the discriminator. And for discriminator, we're going to pass the generated image, right? And then we print the decision. So now you can see it's just some random value that we'll pass it to we'll add the sigmoid layer. Where is it? Pretty sure we'll add the sigmoid layer. All right. Now we don't now we also add the loss and optimizers, right? So can anybody take a guess why is it binary cross entropy? I mean, you don't have to take a guess because
So
the
binary classification.
yes, it's only binary classification.
0 or 1.
Correct, great. It's only binary classification, and we set from logits to true. Why? Because the logits, whatever we get is between 0 to 1, right? So we want to set it, we set from logits to true so that the TensorFlow handles in the background and gives the binary classification. All right, now we calculate the discriminator loss. That is how bad the discriminator is doing. To calculate the discriminator loss, what were we doing? See, we take the classification error, and then we are passing, see in the general picture, we're passing both, right? We pass the real image and the generated image and get the classification error and update the discriminator. Similarly, we take the real image and the output image, I mean the fake image, and then we calculate the real loss, the fake loss, and then the total loss is the real loss plus the fake loss, and that gives us the total loss for the discriminator. Similarly, for discriminator, obviously we only take the fake output that is coming from here. Generator, yes. So the classification error, where is it? Yes, the classification error from the discriminator. So that is only coming from here, and the input for that was what? Fake, right? Whatever it produced. So that goes to the fake output, and then we return the cross entropy of that. And then we set up the optimizers, Adam optimizers. I think this is pretty much straightforward. for both we set the Adam optimizers, and then we create the checkpoint so that after every iteration it gets logged and weights get updated, right? And it goes to the training checkpoint. If you see the file, it should have created. Yeah, see, it has created the checkpoints, and these are the training checkpoints. So this is the basically the model after after every iteration. All right, not after every iteration. I think after every 15. Yeah, after every 15 epochs. All right, and now if we define the training loop, we want to run it for 50 epochs. The noise dimension. Now, what is this noise dimension? Can anybody take a guess? What is this noise dimension basically? So what is the noise dimension? If I quickly come back here, it is this, right? Input to the generator. Yes, excellent. Input to the generator. Now we instantiate those. I mean, we define those variables. So can you share the? Yes, I will definitely share the code. I just want to make sure that you guys at least have a understanding as to what is going on before I share the code. Now, you know the context manager, right? In Python, context manager, we say with open as whatever, file open, write, and etc. Okay, why tanh function you used as activation, especially there in generator? Why not others? So can you tell me where? You mean the tanh function? You mean the activation function, right? Yeah, I've not defined any tanh. So obviously now, see, rekill, relu or completely non-linear, right? Right. So we need some kind of way to reduce the linearity at least at the out, right? So we want a straightforward 0 or no. I mean, yes or no, right? So that's why we use tanh. So tanh, you know how it goes, right? If it's 0, it is, at 0. If it's 1, it's 1. So if you guys see the tanh graph, it goes like this. So that is why for rekill arrow, it goes beyond, I mean, less than 0 and goes like that. Above, yes. So that is the whole point. So we want to reduce the, I mean, we want to increase the linearity, so to speak, at the last layer. That's why. So now we know the gradient tape. Now what this gradient tape does is it basically tracks the gradient after every forward pass, right? To calculate the or to basically do back propagation. Now we want to track two gradients, one for the generator and one for the discriminator. So that's why with two context manager we are running this. So generated image is generator of the noise, and now here we set the training to true because we want to track the gradient. Now before I had set it to false because we did not want to track the gradient, simply because I was just plotting the image just to see how the random image that got generated was. But here, when we want to actually train the model, we want to set the training to true, the real output from the discriminator, and the fake output from the discriminator. For fake output, we obviously pass the generated from the generated images. Generators generated images, right? Don't get confused. So for the discriminator to get the fake output, so we pass the generated images from the generator. And then again, we set the training to true, and then we calculate the loss. So generator loss was given here, right? It takes the fake output, and then discriminator loss takes the real output and the fake output. It calculates. Now here you can calculate the gradient of the generator. So this is where the gradient comes in. Now here you can see the gen tape, right? This thing keeps calculating the gradient after every forward pass. So we say generate gen tapes, that is for the generator, track the gradient for the loss and the training variables. So obviously we are going to do a differentiation for what? From the loss to the trainable parameters, right? Does it make sense? Yes. That's how we calculate the gradient. So we calculate the gradient from the loss to the trainable parameters. So that is the trainable variables. And then for the discriminator, same thing. The discriminator's loss and the discriminator's trainable variables. And then we apply the gradients. We calculate the gradient and apply the gradient to the generator and to the discriminator. And then we start the training. So here we say train step. Now the train step is this. And by the way, at tf dot function is the what do you call this? Forgot. Annotation. Yes, it's called annotations. You can annotate a function like this. And when you annotate a function like this with the tf dot function, what it does is it does immediate compilation, so that the TensorFlow basically does immediate compilation. Usually what it does is JIT, right? Just in time compilation. So when you're running it, it compiles. But if you say tf dot function, when the interpreter, Python interpreter understands that, okay, there is an annotation called tf dot function, it calls the tf function and then it checks if everything is fully handled here, even before, when you just define the function, right? Even before calling it. So if everything is properly handled here, and making sure you don't get any errors, there is just one good way of writing code, especially if you're in your training step. You usually do it just to, because in the training step itself everything comes together, right? Your loss, your compilation, your gradients, all that good stuff. So that is why you use tf dot function as the annotation. And then yes, you call the training function for so many number of epochs. Here start time, you are tracking the time when you started, and then after every 15 epochs, so one epoch is one complete forward and backward pass, and then you generate and save images. That's it. Now here, yeah, it is still training. See, time for epoch now, it is 47th epoch. It's good that I started because we had to wait the entire time. So now you can see how nicely the generator is trying to generate the images. And then after that, we can restore from the checkpoint and then visualize the image. That's it. That's basically it. So if we come back, we completed the entire generator, the discriminator, calculating the gradients, the loss of both the generator and the discriminator. Now training it and then visualizing it. But yes, you guys can check it out. I will share you this link. I will share you the presentation PDF. In that, I've added something called as references and resources that I used, and you can also use to get more insights. But yes, I am a bit over time, 11 minutes. But yes, it is what it is. Now, all right, I hope I have answered all of your questions. I mean, if you guys have any more questions, generally what models can be used as generators and discriminators? Could you please be more specific? What do you mean by what models? Could you elaborate the question? So meanwhile, please feel free to follow me on Twitter and GitHub. What kind of autoencoders for generators? What kind of autoencoders for generators? I'm not sure I understand your question, Sumati. What kind of autoencoders? You mean how is autoencoder and generators related? Is that what your question is? um, Example like UNet, VGGNet. Oh, you mean like, okay, like predefined models for GANs. I mean for autoencoders. Okay. I got it. Okay. You could use variational autoencoders. You could just Google it and check. Right off the bat, the one I can remember in my head is, one I can, that's what, variational autoencoders. So if I say types of autoencoders, you get a bunch of different types of, yeah, you have undercomplete convolutional autoencoders, denoising, like I showed you one. a sparse autoencoder, deep autoencoder, undercomplete. You guys can check it out. There are different sorts of autoencoders, and if you wanted to check the model types of autoencoder models, vanilla autoencoder, multi-layer. Yeah, you guys can check it out. It's just open there. Yes. But you need to understand the basic intuition. Okay, the next question is, so how can we include our own data set to produce GAN images? All right, so what you should do ideally is to use the TensorFlow dataset pipeline. Yes. So here you can see, if you go through this documentation completely, they have told how you could use different types of data. See this tf.data pipeline, handling different types of data, how you could set up the data and all that good stuff. Basically, you just have to make sure your image is of the size that you can handle, or you completely understand. That's all that there is to it. You can basically create a data set of your type, construct, curate the data set, convert it to an NumPy array, and then instantiate it using tf.data.dataset, pass it from tensor slices. Again, same thing, and then pass the NumPy array to it, and then make sure that the model, the type of data or the dimension of data you're passing just matches the input state. That's all. Once that is done, the same thing you can employ. Once that is done, whatever we did here, right? We instantiated the train images, normalized it, of course, created a batch size, and then from dataset.tensor slices, we called it, and then made sure that we kind of completely understood the type of data that was going to go in the down the pipeline, and of course what the discriminator model takes. There are different types of GANs. What we did was deep convolution generative adversarial networks, simply because we used convolution operations, transpose and the normal convolution operations. But there are different types of GANs like PIX GAN, cycle GANs. You can check it out. There are so many different types of GANs. Just feel free to go through the code and how they have laid it out. That should give you a better understanding. All right. Any other doubt? So you guys can scan the QR code. I made your life easier. You guys can just scan the QR code and get in touch with me. Also follow on the GitHub, because GitHub is your new curriculum vitae, right? People see how many.
One doubt.
Yes.
This training of the GAN network is same as that of other deep learning networks?
No, exactly. Good question. It's not exactly the same. Like I said here, for GANs, you have to do a bit more. You need to, create the discriminator loss, the generator loss, and all that stuff, to handle those, to calculate the loss basically. But yeah, only the pipeline that gets changed is to, if you're asking the different pipelines, yes, you need to change the discriminator loss. But apart from that, I think most of the pipeline remains the same for other types of, if you're asking like a convolutional neural network, then yes, it's kind of the same, because the same code you will be writing depending on your use case. But for GAN specifically, you need to make sure that you well define the loss of the discriminator and the generator. And also the output function, the last output function, tan h, that would be something else as well. So that depends on your use case.
It will work on the collab environment?
Yes, it will work on the collab environment.
It take long time or very normal?
No, no, it's fine.
Training time will be training time.
Yes, it takes some time. See, now it got, the model got trained. Where is it? Yes. Now restore. Now it created a restore. Now you can see how it got trained through the iterations, right? Two different iterations. This is basically a GIF. But yes, that's what. It won't take too much time. Make sure your runtime type is GPU. See what works best for you. Generally, GPU is better. TPU, I've seen it. it does not really outperform the GPU, because CPU is, if I quickly do one thing so that you guys can just not text, I just want to code. So if I said -SMI, so this basically gives the compute instance. So we are running a Tesla T4 which has 15 gigs of video memory. So this is better than any other TPU that you can imagine as of yet. So, I think GPU does a better job. Shrikant says, even if we use GPU, it takes more time if we decrease the number of epochs. Yes, just imagine you're getting a trade-off here. It takes more time, definitely, but it doesn't mean that you reduce the epochs, because your model would not have converged to the local minima or the global minima, right? So your model would not have converged, and if you reduce the number of epochs, there is much more possibility that the model can still perform better just by increasing the epochs and not doing any other hyperparameter tuning. But yes, that is it. Yes, it takes time, but conversely, if you were to do this on a CPU, it would take double or triple the time that it took on the GPU here. That much I can say. But anyway.
Okay, thanks.
I hope, yes, thank you. I hope this session was impactful and you guys got something out of this. And, you guys enjoyed the session, although there were some heavy theory involved, but I hope you guys came, you guys got what you came for. Yes, do keep in touch if you want to know more. I will continuously, and like I was saying, continuously keep updating your GitHub profile, because what people and recruiters see nowadays, especially you're in 7th semester, they actually, they see how much contribution you have done to GitHub. Like I said, GitHub is your new curriculum vitae, especially for those computer science students and maybe even IT, right? So just make sure you guys have your GitHub up to date, and keep contributing code and committing code every often. Yes, that is it. If you guys have any other questions, let me know. But if not, thank you, everyone. Thank you for having me. It was a great session.
On behalf of all the participants and staff, I would like to extend a really hearty vote of thanks towards our guest speaker, Mr. Rajat Moradwaj. We are really thankful that you shared your valuable knowledge with us at the event. Hoping to see you again in coming events and workshops.
Yes, definitely. Yes, definitely. Thank you. Thank you for having me, and good luck. Thank you.
Thank you, sir.
So I will take a leave now. All right. Thank you. Bye-bye.